All right, so let's go ahead and start today. We have a note sheet just because there's some graphs, so I think it'll make it go a little bit quicker. Directions are a little bit longer, which actually means usually, ironically, the problems are sometimes a little bit short. And that's just, my joke, but it does seem to hold true. Okay, so what are we doing? Today we're doing continuity. What does that mean? It is continuous. Yeah, I wish you would put this earlier, though it's kind of where books put it, but we've kind of been talking about if things are continuous, okay? And it's as simple as I trace the graph. If I have to pick up my pencil in any way, then it makes it discontinuous, okay? So even though we call it continuity, continuous, we're actually going to talk about where it is discontinuous, okay? And there's basically three ways that I have to pick up my pencil. Okay? So that is classifying discontinuity. And like I said, we kind of have gone through these. Does anyone remember they all pop up? Maybe not the first two for sure pop up on rational functions. Does anyone remember what a removable discontinuity is? When you take out one thing, so that is, we just call it, or I kept calling it a hole. Yeah, that's what I call the hole. That one spot, that one point. Okay, we could write that, I guess. I still like hole, but it's one point being removed. But I still am going to have to pick up my pencil, so that makes it discontinuous. Remember, continuous literally means I can trace the graph and never pick up my pencil. Simple as that. All right. Infinite discontinuity, I hardly ever call it that. I guess that's its official, but that is the asymptote. Infinite, that kind of makes sense, right? Because it means the graph is going up forever or down forever. So that's why they call it infinite. But that's nothing more than the asymptote. And then the jump, maybe that we haven't seen. The jump is where there's actually a space in the graph. There is space in the graph. Space in the graph. Literally, I mean, you probably couldn't use a better word. These two are more maybe official, and so we say hole and asymptote. But this one's right there. There's literally a jump or space in the graph. That one they named the best. All right, so let's take a look at this graph. Can we identify where there is discontinuity? So, I mean, you could literally trace the graph. And there's an arrow, so it's going out forever this way. So I come up. When I hit a hole, do I have to pick up my pencil? Yes, it's literally one spot, but that hole is saying I have to go over it. As soon as I have to go over it, that's a hole. So when we identify, we simply do the x values. So we would say there is a hole at what value? The x value is -2. So you simply state the x value, -2. And then you have to say why we're saying it's discontinuous there, because it is a hole. If you just want to say removable, I should say the reverse, right? If you say hole, that's fine. I think there's probably something on the homework more where you have to choose. So you would choose then the removable as opposed to the hole. But same thing. Do we see it's just different words? All right. So I go there. Now I keep tracing. I have to pick up my pencil to go here. So I have to pick up my pencil. So that's discontinuous there. Give the x value. So x equals -1. Can we see where we're at? Okay, good. -1. Okay, now what did I have to do? What causes it to be discontinuous? It's kind of like that space in the graph. So it is a jump. Right? And then I trace. This goes down. I pick up my pencil. As soon as I pick up my pencil, that's a discontinuity. Why did I pick up my pencil? T asymptote, so that is the infinite. Okay, and where did I do that, or where's the x value? I can put it over here. X equals maybe. Oh gosh. Okay, let's back up for a second. Make sure, did you guys see the -1, the jump? Make sure that you got that. And then the other one is at 2. That's not on there. And then the reason is asymptote or the official infinite. All right, so now it says where it is discontinuous, determine whether the graph is continuous from the left, the right, or neither. Okay, now you gotta shake out of your head domain. We're not doing domain stuff. Okay? The first thing is where it is continuous from the left or right, you have to have a value. So at -2, there is no value. So it is not continuous from the left or from the right. At 2, do I have a graph at 2? No. So it is not continuous from the left or from the right. So you're like, wait a minute, what's going on here? Well, take a look at -1. -1 we said was discontinuous. But do we actually have a graph at -1? You got this point right here, and that's okay. It is discontinuous at -1 because I had to pick up my pencil. But do you see how we would say it's continuous from the left? Because that point is included and it's on the left side of my x equals -1. Let's say that again. Do we see that? These two are neither. So we can go right, if there is no value there, then we don't say that it's continuous from the left or from the right. So I literally wrote -2, neither. Can you see any of that? Okay. And 2 is neither. If there is no graph, then it's neither. So most of them come from these jumps, because whole, right, and asymptotes. We'll talk a little bit about it on the next one, but okay, so -1. There is a jump, so it is discontinuous. But do you see how this closed dot is part of this left side of -1? And so we say that it is continuous from the left. So -1, continuous from left. This might also help, like I think our author, I wish he would have done this down here first, actually. So if you're still on the fence, let's do this part and then let's see if it makes sense. Now state the intervals on which the graph is continuous. So slide it back down. What do we think? It's going to be, now again, shake out of your head domain. There's some similarities, but not the same thing. Okay, so it's different than domain. But we are gonna, where is it continuous? So tracing your pencil, and then I have to jump over, -2. So I need to toss that. So it's going to be -infinity to -2. You only give x values. We actually don't do union. We just literally do a comma. We're just stating the intervals that it's continuous. We're just literally stating the interval. So we're just going to put commas. Now, here's where it kind of maybe makes some sense. Anyone want to try the next interval that it's continuous? -2 to -1. Would I include -1? Yes, because there's a point there. And that's kind of what we're getting from up here, continuous from the left or from the right. This is a great example. So I would say -2, and I would do a parenthesis because there's a hole there. But at -1, I would include it. And that's what we're talking about, continuous from the left. Because what would the next one look like? The next one is going to be -1 to 2. I'm starting here, so am I going to include this? It's an open circle, so on this next one, I'm not going to include it. So I'm going to do -1 to 2. Do I include 2? Asymptote, no. And so look right here at this -1. Do we see how we would say it's continuous from the left, but not from the right? Okay, and that's because of that bracket, which goes along with that point. And then just a comma. And then my last one would be 2 to infinity. It's an asymptote, so it would be a parenthesis, 2 to infinity. And notice here, I didn't do any bracket. So that's why we say it's not continuous from either side. Same thing with -2. I did both brackets, which just means it's not continuous from either side. -1, continuous from the left, because that's where that point was. All right, let's try it. Let's try it again. Same thing, just a little bit harder on the next one because they put this random point here. But let's try. We'll put that point there. Okay. So same thing though, we're going to state where it's discontinuous. Where it's discontinuous, determine if it is continuous from the left, right, or neither. And we can also state why. I did, yeah. So they may on the homework too. All right, who wants to give the first discontinuity? Someone's got to try. Perfect, perfect. She said there is 1, okay. 1, 2, 3, 4. This is -4. There's a hole there. Perfect. So x equals -4. We could write hole. We could write removable if we wanted to. Either one's okay. See any of that? I might zoom out a little. All right, who wants to give the next one? Who wants to try? Perfect, perfect. Yeah, it is, yeah, for sure at -2, right? There's a jump, right? So you just trace. Every time you pick up your pencil, you gotta stop and say where you're at. I pick up my pencil here, and I am at -2. X equals -2, and that is, I think you said it, right? That is a jump. All right, now where's the next one? Trace, 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 trace. I have to pick up my pencil. What X value am I at? 3, beautiful. And that is a jump as well. I'm literally moving the pencil up to a different spot, so that is a jump. A space in the graph. Do you see how there's nothing there for a while? All right, we trace down. It's kind of weird. There is a point there, but to touch it, I have to pick up my pencil. So it is definitely a discontinuity. What value is that? 5. And there is definitely space here. So we would consider that a jump. And then I think we're good. Then we go, and then we stop. Okay, oh dear, can we see all, oh, can we see 4? Okay, now let's go back. -4, is it continuous from the left, right, or neither? And I know it's a little confusing because the graph isn't coming up, but how would we classify that? There's no graph at -4, so we would say it is neither. All right, how about -2? There's definitely a jump, so it is discontinuous, but there is a graph at -2. And the whole, right, when I'm talking about -2, it's not really an asymptote, but I can like draw in, maybe I should draw in a solid line. It's continuous to -2 on that left side. So we would say continuous from the left. You see any of that? Okay. All right, how about 3? There is a point there. And what side of the graph does that point go with? It goes with the right side. So this is continuous. I want you to at least see one, continuous from the right. Questions on that? Do we see how this point, and then it keeps going on to on the right side? So that's continuous on the right. All right, anyone want to take a guess? We do have a point here. So now this is kind of like the exception. We do have a point here at 5. But so I'm down here, I have to pick up my pencil to go here, and then I have to pick up my pencil again. So that is neither, right? So that one's kind of a weird one. There is a point there, and don't worry too much. This is kind of technicality. The main thing is you understand continuous means it's a flowing graph. And most of the stuff we see is continuous unless it has a hole or an asymptote. Very basic stuff, but really that's what we see by far the most of. In fact, notice I'm giving pictures. I'm not giving equations, because in order to do something like this, it would have to be a piecewise function. It would have to be a whole bunch of pieces of graphs put together. But if this makes sense to you, this is a jump and this point is isolated. So it's definitely not continuous from either side. All right, how about intervals? And again, this might help show it too. And let's talk about what do we do with that isolated point as far as stating if it's continuous. Let's light it up a little. I think we can kind of get both there. Okay, so this time we do have a closed dot. We actually have a start. Where is that? -6? Okay, so close -6. Do we see why it's a bracket? There is an official point there. -6 to -4. Remember, this isn't domain. We're just going to state intervals where it's continuous. Okay, just literally, where do I draw my pencil before I have to stop? Comma. -4 to -2. Since there is a point there, I have to put the bracket. And that's why it's continuous from the left. Who wants to do the next one? -2 to what? To 3, and it's both parentheses because there's open circles on each end. Next one. Yeah, okay. 3 to 5. 3 to 5. Close on 3. It is in fact a bracket on 5. And even though there is a value at 5, it's an isolated point, and so it has nothing to do with being continuous. So our next one would be a parenthesis, because this is an open circle. We really don't care about isolated points at all. We get no respect. All right, why are they there anyways, right? They're 1 point, get them out of there. All right, so they get no respect. So 5, a parenthesis, and then where do I end finally? 9, and 9, we do a closed bracket just because there is a point there. Stop. So remember, it's a little bit different than domain. 5 would be in our domain, okay? So try to kind of keep these separate. That's the only thing I don't like about this. I don't want you to confuse it with domain. But notice, and here, this will kind of take care of this stuff too. Do you see how -4 is neither? Because we use parentheses. -2, a bracket on the left, so continuous from the left. 3, oh yeah, I'm like, wait a minute, but this is a bracket. Can you see that? And it's a bracket on the right, so continuous from the right. And then 5, and that one might have been hard to even do down here, but 5 is a parenthesis on both. And that's why it's needed. Like I said, don't panic completely, give it a try. Main thing is right now, keep it isolated from domain. Okay, this one is just, and on the homework, you just have to click around. Can you do the reverse? Can you draw a graph? Now, not everyone's graph is going to be the same, but everyone's graph has to have these specifications. How are we doing? Okay, we're not sure. I think we're going to finish early. So if people want to stick around and do their homework, they can, or you can definitely, you know, find time these next couple of days to ask. But we still have, yeah, we still have a little bit. Okay, we change gears here. So let's do this one, and then we'll change gears. Okay. So draw a graph that has a removable discontinuity at -1. So what does that mean? Removable discontinuity means a hole, or one thing out. So at -1, I have to have a hole. You can literally put it anywhere as long as the x value is -1. Let's put it here, but it doesn't really matter. And then the only other thing, and these are the two most common, so that's probably why it's on there. A jump, oh no, this one I don't like as much, but that's okay. A jump at 3. A jump at 3. So I put a 3, I have to go x equals 3. What is the jump again? The jump means that there's going to be a space in that graph. We have to have a space in the graph, and it has to be continuous on the left. So that means I'm going to have a closed dot and an open dot. From the left, am I going to go up to the open dot, or am I going to go down to the closed dot? I got to touch the closed dot because I'm coming up from the left. I'm sorry, it's continuous from the left. Continuous from the left means that I have to go to the closed dot. Now, if you had a reverse, if you have the closed dot up here, that's fine. You just have to draw your graph to that closed dot. And then I could curve this up. It keeps, I don't know, we could go either way if you want to do like an asymptote, whatever you want. Doesn't really matter. And again, if you had your closed dot up here, that's okay. Your graph just has to go to the closed dot because it's continuous from the left. Actually, I got to go this way. From the left. All right. Now, don't forget, why do we care about where graphs are continuous? We got to bring it back to limits if we're in chapter 1, okay? Okay, so let's see, did we do okay? Yep, we had the jump there, so that's okay, continuous from the left. Okay, so it's okay. All right, why do we like where it's continuous? How do we evaluate limits if it's continuous? Three words, right? Plug it in, okay? Remember, if it's continuous, no matter what it looks like, it's great. Okay, you just plug it in, you get a number. As long as it's not making the bottom 0, we're at a place where it's continuous. And the easiest way to evaluate a limit where it's continuous is plug the number in. Okay? So he kind of comes back and reminds us that. I think we've been doing that, so I think we're pretty good. So don't let this intimidate us if we're doing the limit at 9. Now, it's possible, I don't think this one is, but it's possible that somewhere that graph is discontinuous. But as long as it's not discontinuous at 9, that's good. Okay, we're just doing individual places. Maybe I won't say points, but we're doing individual places. If it's continuous at that individual place, plug it in, that's your limit. Okay? So as long as I don't get an answer of 0 on the bottom, I can evaluate the limit by just plugging it in. And that For the most part, there's maybe some exceptions, but for the most part, that means it's continuous. So he doesn't want you to forget that evaluating limits where it's continuous, piece of cake. Okay? So 4 plus 3, and that gives us what? Square root of 16. What's the square root of 16? 4. Okay, now we've been doing a lot of canceling. Do the 4s cancel here? No, because that addition, right? Our operation that we used to like is now the least favorite, right? You cannot cancel if you're adding, but it's not that bad. So it's going to be 7/4. Okay, so piece of cake, we plug it in. What does that 7/4 mean? What does the limit, what does that mean? We're going to get full credit on the test, but we want to kind of make sure mentally, what does that 7/4 mean? This graph is continuous. And when X is 9, Y is 7/4. And the limit means that it's also approaching both sides of 9. As we come closer and closer to 9, both sides of the graph are approaching 7/4. All right, we got to do a trig. We got to make it a little bit harder. All right, but we don't even have a fraction. So we can, there's a good chance that it is continuous. So let's plug it in. Let's see what we get. Now just parentheses all over the place, so be careful here. Cosine of pi over 2. But if it's continuous, you just got to plug it in and evaluate. Okay. If you need a calculator, that's fine. Pi over 2, does anyone know where pi over 2 is? At the top there, pi over 2 is here. And so that point is 0, 1. 0, 1. Cosine is cosine the X or the Y? Cosine is X value. Cosine is X value. So start here. What is cosine of pi over 2? The X value, which is 0. So we got cosine of parentheses pi over 2 plus 0. This guy goes to 0. It's asking for the X coordinate at pi over 2. Well, that's easy. Pi over 2 plus 0 is pi over 2. So it looks confusing, but it's really asking for cosine of pi over 2, which we just got done telling them. It is 0. And 0 is an okay answer. Maybe that was a good one just to remind us that 0 is an okay answer, because that's a Y value. The answer to a limit is a Y value. Can a Y value be 0? That's fine. Yeah, a Y value can be 0. It's just in a fraction, the denominator can't be 0. But a Y value of 0 is fine. So when we if we graphed this, the X value is pi over 2, the graph is approaching both sides the Y value of 0. All right, what about this last one? Do I want to factor? Doesn't matter. If you see this and you factor, that's fine. Okay. If you see that when I plug in 4, I don't get a denominator of 0, that's okay too. Because the only difference between this graph, and if we actually factor it and cancel would be the whole. And where's the whole at? If it cancels, the whole is at -5. Now, what happens if we factor? Okay, here we go. Who remembers the rationals? What happens if we factored this and it didn't cancel? Whatever makes the bottom 0 after canceling is that's an asymptote. It's an asymptote. So without factoring, -5 is either, because that's what makes the bottom 0. It's either a whole, and it's actually going to be crossed out, or it's an asymptote, because it's going to stay on the bottom. But -5 is the issue. And look where they're asking me to evaluate. They're asking me to evaluate it at 4. So at 4, it's continuous. Okay, so you can plug it in here. If you want a factor, you can still do that either way. We could do both ways. So 4 squared plus 8 times 4 plus 15 over 4 plus 5. Okay, so 16 plus 32 plus 15 over 9. I think that is 63, 11, 12, 13, yep. 63 over 9, which takes us to 7. So if we graph this, when x is 4, the y value that it's approaching from both sides is a y value of 7, okay? But if anyone said, hey, this looks like that awesome trinomial, and they just started factoring, what multiplies to 15 but adds to be 8 is 5 and 3. This confirms -5 is in fact a whole. Okay, -5 is a whole, and that's okay. I can still cross it out. I can still do, we could rewrite it if we want though. I'm still doing the limit as x approaches 4. So now I just have this of x plus 3. So maybe now it's easier to see that, hey, it is in fact 100% continuous. What happens when I plug the 4 in? I do get 7. This graph and this graph, the only difference is this one has a hole when x is -5. That's the only difference.
So this one would be graphed.
Say that again?
So both of them would be graphed.
Yeah, because notice I should have got the same thing either way. So I got a 7 either way. Yeah, and so you can do it either way. If you're thinking like if you happen to factor it, doesn't matter at all. And in fact, you might want to factor it because if it was asking for the limit at -5, then you would have had to factor. -5 causes the bottom to be 0. So when we factor and cancel, we're filling that hole in. All right. This is just a reminder, if it's continuous though, at that specific value that we're asking to find the limit, just plug it in. Okay, we got one last thing. This intermediate value theorem. This comes up a little bit. Now, the first thing is your function that you're given must be continuous. Okay? If it is continuous, okay, on this interval from A to B. So let's draw down here a little bit of graph. What's going on? We've got this interval from A to B. Now, n is between f of A and f of B. F of A and f of B are y values. So if I plug A into my function, my f of x, I get an f of A coming out. And if I plug a b into my function, I get an f of b coming out. So this is f of A and this is f of b. Could they be reversed? Could f of A actually be on top and f of b actually on the bottom? Yes. I have no idea. They're just spitting out two values. Okay. So it doesn't matter which one's on top. If you put it on top, don't erase it. It's fine if f of A is on top. Doesn't matter. What they're saying is there's an n between them. That's all they care about. So it doesn't matter which one's on top because there's an n between them. Okay, so n is between f of A and f of b, as long as they don't equal each other. That's all this is saying. Then there exists a number c between A and B. So somewhere, doesn't have to be in the middle, but just somewhere between, there's a c value that produced this n. There's a c value that produced that n. And that is called then f of c. So let's say, well, that's right. Okay, so you guys are saying like, okay, that's great, right? All right, so let's kind of apply this. So one place that we use it a lot. I kind of like to say, if it's continuous, let's put some points. So this was the start and this was the start. If it's continuous, like if the domain is continuous, then the range has to be continuous. Does that almost make kind of some sense? Saying if I got something left to right, then I also have to have something up and down. If I have something left to right, then I have to be able to fill this space somewhere on my graph up and down. Again, all because it is continuous to begin with. All right, this is where we care about. There's a couple places where we really like the intermediate value theorem. What happens? Let's take a look at my graph. Let's go. Let me go back to this. You guys can just look. Was f of a, the place that I put it, was f of a positive or negative? Is that y value positive or negative? Positive. My f of b, also positive. But what happens, this is where we use it, what happens if f of a and f of b change signs? What happens if one of them was negative and one of them was positive? If it's continuous and I go from a negative to a positive, what number did I have to go through? 0. And that's what we actually care about. We actually care about that goes to 0. Same thing. What happens if my f of a was positive, but my f of b was negative? I know that I had to go through 0. And that's actually what we care. We actually care about where we go through 0. They're called, let's see, finding the roots. Roots are also called x-intercepts. See. Can you even see that? No. And they're also called zeros. Roots are also x-intercepts, and they're also called zeros. And we care about those a lot. I mean, think when we were graphing those rational functions, what did I make you find? An x-intercept and a y-intercept, but we care a lot about x-intercepts. So this can help us at least narrow down where the graph is crossing the x-axis. Oh, let's see, do I want any pictures for this? Okay, we could draw, so we could even draw that same picture, but this time, so here's my A, and here's my B. But what happens if my f of A is down here and my f of B is up here? So f of A A produced f of A. A produced f of A. B produces f of B. My graph is continuous, so that means I got to go from this point to this point. I've got no choice but to go through the x-axis. Okay? I could draw it like this. Someone else could say, hey, I think it goes like this. But what do I have to go through? If I go from A to B and I know it's continuous, so I can't pick up my pencil, I got to go through the x-axis. Okay, so this is what the homework is. It's a little bit more of a process. Use the intermediate value theorem to show that there is a root somewhere in this interval. So you got to show to me that there is an x-intercept or a root or a 0 between 16 and 25. So the first thing you do is you have to tell me that it is continuous. Is this continuous? On your own on the test, there is one of these. And you have to at least say, yes, I am confident f of x is continuous. Okay? Now let's think. The only thing that would cause trouble is a square root. And we can't have negatives under the square root. But we're putting in numbers 16 through 25. So 16 through 25, is that going to cause us any problem with the square root? No. So I'm pretty sure that it's confident, or pretty sure it is continuous. Why, if I put it on the test of polynomial, why do we love polynomials? Because they are continuous, okay? So on the test, if it's a polynomial, you say, hey, polynomials are continuous, okay? Here, I mean, we could say something here like x has to be greater than or equal to 0, but for the most part, as long as you tell me that you took some time to think about that this is continuous, f of x does have to be continuous. Not throughout the whole thing, but just continuous between 16 and 25. Oh, actually, sorry, it should actually be brackets. We actually have to include those. So we don't care if it's, you know, this is not continuous. There isn't even a graph at -5. But all we care about is between 16 and 25. Okay, then we do f of 16. We literally go get the y value. We're actually going to get the y value. What is f of 16? 3. Square root of 16 minus 16 plus 5. So this gives us, okay, so this is what? 3 times square root of 16 is not 8, 4. Minus 16 plus 5. So that gives us 12 minus 16 plus 5, which gives us 1. Are we okay going right to that? All right. Does anyone want to know what we do next, or does anyone want to say what we do next? We found f of a, so to speak. Now we find f of b. Yes, someone said f of 25. Beautiful. F of b, which is in fact 25. Yeah. This would give us, are we okay on that one? This actually gives us what? -4, but then plus 5, or if you type the whole thing into your calculator, that's fine, but that should be 1. Okay, so now we plug in 25. Good. Oh, okay, so that gives us what? 3 times 15 minus 25 plus 5. So 15 minus 25 plus 5 should take us to -5. How did I just show there's a root? We went from positive to negative. Okay? Is it okay if it would have went from negative to positive? Yes, I just have to show that sign change, okay? So what I do is I usually circle these and I say there was a sign change. Sign change. No. Sign change, okay? So show your 2 answers, show that there was a sign change. Then does anyone know what these 3 little dots mean? A triangle and a dot means therefore there is a root. And we could even say therefore there is a root. Maybe we should say in this interval 16 to 25. And now I can actually change it from brackets to parentheses, because a root means it's 0, and I know at 16 it was 1, and at 25 it was -5. So I know that it's not even a 0 at 16 or 25. I know it's literally in between those 2. Now, can anyone think why we like this one even better? Because, and again, you don't have to come up with these numbers on your own. They're going to give it to you. But how great is it knowing that there's a root between the integers 3 and 4? I mean, we've really narrowed it down. It's great. I mean, it's still great that we narrowed this one down between 16 and 25. But narrowing it down to between 3 and 4, we could even probably estimate, you know, at that point. All right, so the first thing we have to do, same thing, let's just do it one more time. This is absolute value. Does anyone know what an absolute value graph is? A V. Yep, a very sharp V comes to 1 point. Is that continuous? Yes. Absolute value graphs are continuous. So we probably should say something like that. Absolute value graphs are continuous. We actually only care about, if it was discontinuous at 7, would we care? No, it only has to be continuous for this, especially this problem between 3 and 4. But absolute value are continuous wherever. But if for some reason it just has to be between 3 and 4. Okay, and then what do I do next? You actually plug it in. Yep, you're going to do f of 3, get an answer. So that gives us what? 2 times 3 is 6, minus 3 is 3. The absolute value of 3 is still 3. This is multiplication. So 12 minus 17 gives us, give us -5. What do we really care? Our first answer was negative. Okay, that's what we care about. So if I'm going to prove there's a root, what am I hoping for when I plug in 4? It better be positive. If not, then I just tell someone, hey, it's not a root, or there is no root between here. All right, so f of 4. Let's see if it can give us. Let's see, what are we doing? 2 times 4 minus 3, and then minus 17. That gives us what? This gives us 8 minus 3 is 5. Absolute value, don't change the sign. It's just always positive. So it was positive to begin with, so that's okay. 4 times 5, beautiful. That gives me an answer of 3, right? And there's some room for leeway. As long as you get something positive, you're in good shape. What does -5 and 3 represent? The y values at the beginning and the end. So if the y value at the beginning was negative and the y value at the end is positive and it's continuous, I had to have gone through 0. Okay, there's just no other way. So I just say something like, hey, I did have a sign change. Therefore, can you see any of this? There is, not only is there a root, but specifically between 3 and 4, between my 2 numbers. Did I find the root? No. Did I narrow it down? Yes. At least I have some direction on where to go. Okay. All right, so give that a try. Homework's on WebAssign. You did not finish early. I don't know why. One of these days I just have to realize. So let me say this while you're packing up though.